In this video we will solve the exam of January 2019 with the exception of the questions or sub-questions that are related to theoretical matters because they are covered by the video course. So here's the first question. The first question is, give a definition of the four fundamental subspaces. That's covered by the theoretical course, and then find bases and dimensions of all four fundamental subspaces of the matrix that is shown. What is the rank of the matrix, and express the third column of the matrix in terms of the other columns. Then there is a question about the use of these four subspaces, and this is also covered by the theoretical course. As usual, try to do the exercise by yourself and push the pause button. So what you have to do is use the Gauss-Jordan elimination, right? What we do is obtain an augmented matrix, and here in the first part we have the A matrix, and here we have an identity matrix, right? So we'll do Gauss-Jordan on this matrix, but at the same time we'll do it on the identity matrix, and at the end of the process we should have a matrix here that is in row reduced echelon form, and what we'll have here is the elimination matrix. If you use this elimination matrix to pre-multiply A, you will obtain this matrix. So let us start with the first pivot, and we have to create zeros below this pivot. So we use elimination, right? Two elementary row operations. The multipliers are easy to obtain. It's the element to eliminate divided by the pivot, so we have multiplies 1 and 1, and if you do the computation, this is what you obtain. Then we look for the next pivot in this second row, and you can see that it is not in the second column but in the third column, and so we have to create zeros above the pivot and below the pivot, and again we'll do row operations. The multipliers are this one to eliminate divide by 1, so -1, and here this one to eliminate divided by the pivot, so a 1. And if you do the calculations, this is what you obtain. And you see now, because we have a row of zeros, there is no pivot in the third line row, that we are here in the final stage, right? What we have here is a matrix which is the row reduced echelon form, and here we have the elimination matrix that you can use to obtain this row reduced echelon form. There are two pivots that are non-zero, so the rank of the matrix is 2. You can read from this fourth column here that the fourth column is a linear combination of the first one, which is a pivot column, and the third one, which is also a pivot column, and you have to take 1 times the first pivot column plus 1 times the second pivot column. So this is what is written over here, and if you isolate C3 you obtain this relation here. So C3 is C4 minus C1, and it's not depending on C2. So now we'll have a look at the basis of the column space, and remember that this is all possible combinations of the column of A. There are 2 pivot columns, so the base is obtained by taking the corresponding columns in the original matrix. You cannot take these ones because we have done row operations, and the column space of this one is not the same as the column space of this one. By doing row operations we have not preserved the column space, so it's very important that you take linear combinations of the corresponding columns in the original matrix, and this is what you obtain here. You should always check that you have vectors here in the base with 3 elements, because of course if you combine columns you should have here basis vectors with 3 elements. right? So now let us have a look at the left null space, right? And the left null space can be easily obtained from the elimination matrix. If you use this vector over here and you pre-multiply A, you will obtain a 0 vector, right? So the left null space is a combination of this vector, so it's this one pre-multiplied by a scalar gamma. Again, if you pre-multiply A, you should have a vector with 3 elements, right? So in this case, the null space is obtained from basis vectors with elements, number of elements that correspond to the number of rows. We know that the column space and the left null space are orthogonal, so you should check that this one here is orthogonal to this one and that this one is orthogonal to this one. Now we have to look for a basis of the row space. The row space is, well, all possible linear combinations of the rows. So we should have here basis vectors with 4 elements. And here, since we have done row operations, you can take the basis from the original matrix or from the row reduced matrix, right? So we have to take linear combinations of the rows that correspond to pivot rows. This is what you obtain if you work with the rows of the original matrix, and this is what you obtain if you work with the rows of the row reduced echelon form. And then we have to look for the null space. These are all vectors x such that ax is equal to 0. If you write ax, well, x must be a vector with 4 elements, and this is indeed the case. So what we should do here is rewrite this by swapping the columns over here, and then you can write it as an identity matrix, an F matrix 0 and 0, and in our case here the F matrix is 2 1 0 1, and we had seen that to construct this null space we could use a matrix N that was, well, minus F with an identity matrix. But then we have to take into account that to obtain this form we had to swap these 2 columns. So what we'll have to do is swap these 2 rows. So this is this systematic way to obtain the column vectors of the null space. Of course, you should check that A times this vector produces a 0 vector and A times this vector produces a 0 vector. If you do the calculations, you will see that this is indeed the case. We know that the row space and the null space are orthogonal, so this vector should be orthogonal to this one, and this vector here should be orthogonal to this one and this one. So here's the second question. Find the values of k for which the system of equations ax is equal to b as solutions other than the basic solution, that is the origin. You can see here that the independent term here in ax is equal to b is identically 0, so you can see that, well, x is equal to 0 is always going to be a solution of this system of equations. And the question is, are there cases for which, well, you will find other solutions than just this one, and this would correspond to cases where the system has an infinite number of solutions. And then for this, or these values of k, we'll see, express the solution in full detail. So when you have a problem of the type ax is equal to b that depends on a parameter and that you need to discuss, well, based on the values of these parameters, well, you have to put this system ax is equal to b in its augmented form, a B, and then what you do is Gauss elimination to bring the augmented system in echelon form, not row reduced echelon form, but just echelon form. So what you do is create zeros below the pivots, and once you have done this, you can start discussing based on the value of the parameter, in this case k, and distinguish between the cases where you have a single solution, no solution, and an infinite number of solutions. In this case, it will be impossible to have a case with no solution, since B here is a zero vector. So let us start with our augmented form. Here we have the pivot. We create zeros below the pivot, and the multiplies will be 1 over 2 and k over 2. If you do the calculations, this is what you obtain. You have here a new pivot. We have to create a 0 below the pivot. So elementary operation with a multiplier, that is 1 plus k divided by 1, so that's a multiply k plus 1. If you do the calculations, this is what you obtain, and here, well, you'll have to do the calculations. It's not that difficult, right? So you can see here in this line that if you take a value of k that makes this one 0 here, and this corresponds to minus 6 over 7, you have a row of zeros over here and a 0 over here, so this corresponds to an infinite number of solutions. So now we have to express this solution in full detail. So we'll start from this one and plug in the value of k here, minus 6 over 7, and this is what you obtain. And to express the solution in full detail, what we should do is, well, bring the whole system now in row reduced echelon form. So we have to create a 0 above this pivot and make sure that all the pivots are 1. So let us start by doing this row operation, creating a 0 over here. So the multiplier is this one divided by 1. As you can see, this is what you obtain. And to have a pivot that is 1, well, you should multiply the first line by a half, and now we have our system in row reduced echelon form. This is F over here, and this is the identity matrix, right? So what we should do is look for a particular solution. This is quite easy, and then we have to look for, well, the basis of the null space, right? And then the overall solution will be the particular solution plus a linear combination of the vectors in the null space of A. Here, how can we obtain a base of the null space? Well, we take minus f over an identity matrix, but f here is just a vector, so in this case this identity matrix, it's just a scalar, right? So minus f with the scalar 1, this is what you obtain. You take this one plus alpha times this one, and you obtain the solution here, in this case where k is equal to minus 6 over 7, where you have an infinite number of solutions. In other cases, and when k is different from minus 6 over 7, well, you'll have this solution over here. Well, let us have a look at the third question, which is probably the most difficult question of the exam. So measurements have been taken on the segment AD, and as you can see, you have 3 measurement sets, and in each measurement set we have measured AD, AC, BD and BC. So the question is, give your best estimates of AB, and we can call this one x1, BC, we'll call this one x2 here, and CD, and we'll call this one x3, right? And you have to do this in the most efficient way, because you'll have to solve that type of problem many times, right? So the hint is that you have to write this problem in matrix form, and you can already see here from the words best estimate, and that the fact that you have to estimate 3 variables from 4 measurements, that this is a least squares type problem, right? And since you'll have to solve this type of problem many times, here in this case you already have to solve it 3 times for different measurement set, suggests that you should use the QR decomposition somewhere, which is a efficient way to solve a least squares problem if you have, well, problems of the type ax is equal to b, right, where you have, well, cases where a is staying the same and b is changing. So here you can see that x will be composed of 3 variables, this length, and this length, and so this matrix A will have 3 columns, so n is equal to 3, and yes, you have 4 measurements, right? Well, m will be equal to 4. So I have helped you a little bit in the solution of this exercise, so push the pause button and try to go further. Well, let us write this problem in matrix form. We had defined the variables x1, x2 and x3 for the lengths AB, BC and CD, and if we look at the first measurement set, we can have a look at the problem. We can see that AD is 25, so AD, that's x1 plus x2 plus x3, and that's 25. We see that AC, and that's x1 plus x2, is 15. So this is the second equation here. We see that BD is x2 plus x3, that's 15 as well. And we see here that BC, but that's the variable x2, is equal to 9. So we have here a system of equations, 3 variables, 4 equations. So this is a least squares problem. We can of course write this in matrix form, right, as follows. You can see here that the first equation will be x1 plus x2 plus x3 is 25, right? And here you obtain the system ax is equal to b, our least squares problem for the first measurement set. But of course you can see here that if you replace b1 by b2, you have the system of equations for the second measurement set, and if you do replace b1 by b3, you have the system of equations, so the least squares problem associated to the third measurement set. So what we'll do here is work with ax is equal to b, and we'll write b1, b2, b3, b4. So we have a least squares problem, and we have always the same a, but the b is changing. And we have seen in the course, and if this is a surprise, you should go back to the course, that you can use the QR decomposition to solve this kind of problem efficiently. So I suggest that you pause now and that you try to obtain the QR decomposition of this matrix A that will need to solve this least squares problem efficiently. Well, let us have a look at the QR decomposition of A. As you remember, we keep the first column of A, and then we have to take the second column and remove its projection on A1 bar. So this means that you have to know how to find the projection of a vector on another vector. So if you take A2, this is what you have, and you have to remove the projection of A2 on A1 bar. This is A1 bar here, and then you take A2, this one over here, you take its scalar product with this one, you have 2. The length of this one squared is 2 as well, so you have 2 over 2. If you do the calculation, this is what you obtain. You should always check that this one is indeed perpendicular to this one. Let us continue. We take the third column of A and we subtract the projection of A3 on A1 bar, this one that we have constructed here, and you subtract the projection of A3 on A2 bar. It's the projection on A2 bar, not on the projection on A2, right? So do not make a mistake here. It is the projection of A3 on A2 bar that you have to remove. So if you go through the calculations, so here you have A1 bar, here you have A2 bar. If you take this scalar product here, this one with this one, you have a 1. The length of this one squared is still a 2. Then you have to take the scalar product of this one with this one, right? This is a 1, and the length of this one squared, this is a 2. If you go through the calculations, this is what you have: a half minus a half, a half, and minus a half. Then we have to compute the vectors q, so we have to take the ones that we have found here and we have to normalize them so that we give them a length of 1. And again, I've forgotten, you have computed this one, you should check that it is indeed perpendicular to this one and perpendicular to this one. Once you have given them a unit length, notice that this one has already a unit length, then you can construct the matrix Q. It's just stacking Q1, Q2, and Q3, one next to the other. You remember that A is equal to QR, so if you pre-multiply this matrix by Q transpose, this is what you obtain, right? Remember that Q transpose Q is an orthogonal matrix, so this will cause or create the identity matrix. So to compute R, we take Q transpose, this is this matrix over here, Q transpose, right? And then we multiply with A, and we should check this again, a matrix of this form that is upper triangular. So we have obtained a QR decomposition for the matrix A that is underlying this problem. Here you have the Q matrix and here the R matrix. So the original problem had been, well, described using the system of equations AX is equal to B, 3 parameters, 4 constraints. So this is a least squares problem. We replace A by QR, we multiply the equation, pre-multiply by Q transpose, and as Q here is an orthogonal matrix, Q transpose Q by construction is the identity matrix, and you obtain this system of equation. And what is nice is that R here is in upper triangular form, so it's ready for back substitution. Here you have Q transpose B that you can compute, right? If you multiply the two first equation by square roots of 2 and the last one by 2, you can even simplify and you obtain this system of equations. As I said, it's ready for back substitution. And then when you have a problem like this one, even if you have more measurement sets, well, you can use this one and this will greatly simplify the calculations of the least square estimates. In this case, I've made sure that in each measurement set, well, what you have here on the right hand side of the system of equations is always 40, 24 and 16, and then you can easily compute x1, x2, x3 by back substitution, and this leads to this least squares estimate for the 3 measurement sets. Here is the fourth question. Find the values of b for which the matrix that is shown is positive definite. For the value of b is equal to -1, and should of course check that b is equal to -1 is in your set of solutions. For the first part of the question, compute 2 decompositions, factorizations R transpose R of the matrix A, one related to the pivots and one related to the eigenvalues. And then there's an additional question: where is the concept of positive definiteness used in the second part of the course? And this second part of the course is of course state space control methods. And for this theoretical part of the question, well, you can have a look in the video course. So the first part of the question is to find the values for which this matrix is positive definite. You will remember from the course that there are many ways to check that a matrix is positive definite. You should go and have a look. One of the methods is to have a look at the upper determinants and check that they are all positive. We could also have worked with the pivots, and for that you need to do elimination on this matrix. So you can see that the first upper determinant is 2, the second one here with that is 2 by 2, it's 3, and then we have to compute the determinant of this matrix. This is a way for me to check that you can indeed compute determinants, and here the easiest way to work, but there are probably other ways to obtain the answer, is to do column operations. So here I've replaced C2 by C2 plus 2C1 in order to create a 0 over here, and the third column I've replaced by the sum of the two columns over here to create a 0. And now what we can do is create a determinant over this line here, and only this one will give a contribution, right? So since this one is on the second line, first column, and if you add the indices you have 3, well, we'll have to multiply the corresponding determinant by -1. So we have -1 times -1, and then this determinant here to compute. If you go through the calculations, you have to impose that this second order polynomial is positive. So the first thing that we do is to compute the roots, right? And the roots are given over here, and you can see over here that if you have a very large b, that this will be negative, right? So the region where this one is positive has to be between the roots. So the matrix is positive definite if b is in this interval, and you will see that b is equal to -1 is indeed in this interval and will lead to a matrix that is indeed positive definite. So from now on we'll continue with this matrix here where b has the value -1. So now we work with the value of b equal to -1, and we want to obtain the factorization R transpose R related to the pivots, right? So we write the matrix and we have to do elimination, and we apply the Gauss elimination procedure to create zeros below the pivot so that we can obtain a matrix in upper triangular form, and this will be our matrix U. And if you do this correctly, so that you do eliminations with a minus over here, well, you'll have the multipliers and you can simply plug them in, well, an identity matrix, and by writing the multipliers at the correct spot, you will obtain L, right? So let us start this. This is the first pivot. We want to create zeros, so the multipliers will be the element that you want to eliminate divided by the pivot. So we'll have 2 multipliers minus a half, right? If you go through the calculations, this is what you obtain. The next pivot is this one. We want to create a 0 below this one. The multiplier is simply the element to eliminate divided by the pivot, so we have a third. And if you do the calculations, this is what you obtain. This matrix is in upper triangular form. You can see that this matrix is indeed positive definite because the pivots are positive, right? So this is the matrix U. So we can put in the multipliers. This multiplier here is to create a 0 over here, so we'll put it at this spot. This one, we'll put it on this spot. It's used to create a 0 over here, and this one here is used to create a 0 over here, so we'll put it here. So now we have the matrix L, and of course it's not done over here. You should multiply L and U, and of course you should obtain the matrix A. Since this matrix here is symmetric, right, one of the first things that you have to check if you have a matrix and you want it to be positive definite, well, it should at least be symmetric. Well, we have now our decomposition LU, but for symmetric matrices you can write a decomposition LD, diagonal matrix, L transpose, and in this matrix D you have the pivots on the diagonal, right? So now this is all we need to write A in the form R transpose R. So you can see here that if you choose R to be the square root between quotes of this one times L transpose, well, you have your R. Okay, so this is what we do. What we mean by square root of D, it's a diagonal matrix where we have the square roots of the pivots on the diagonal. Since by definition, if the matrix is positive definite, these ones are positive, well, the square root is indeed well defined. Then we multiply this square root of D by L transpose and we obtain R. Well, let us now have a look at another factorization R transpose R, one that is related to the eigenvalues. So we need to compute the eigenvalues of this matrix for B is equal to -1, right? So we have to compute the determinant A minus lambda I and then compute the roots of the associated polynomial in lambda. This is the determinant. What we have done here to make things simple is to add the first two columns, as you can see over here. So C1 is C1 plus C2, and the reason why we do this is that we have a 0 here and we have 1 minus lambda in the other two elements. So we already know here that lambda is equal to 1 is going to be an eigenvalue. So let us construct the determinant using this column, and if you go over the calculations and you factorize, you can see that you can write this polynomial like so, and we can see that we have here an eigenvalue 1, 2 and 5, and without a surprise the eigenvalues are positive. This is normal because this matrix is positive definite. So here, if you have an eigenvalue that is negative, well, you should check your calculations if you know that the matrix is positive definite, right? So here we have to find the associated eigenvector, and you know that for an eigenvector you have A times the eigenvector is equal to lambda 1 v1. So this is equivalent to checking that this is equal to 0. So this is the system of equations that you obtain. Here we have done a few row operations to simplify things, and here you can see from this last equation that v13 is equal to 0, and from the first equation you can see that v11 and v12 should have the same value, so we have chosen them 1 and 1. You can do this for lambda 2 is equal to 2. This is what you obtain. This is the system of equations that you obtain. Here we have fixed v21 to 1, and by looking at the second equation you can see that v23 is equal to 1, and then by using the first equation you see that v22 is minus 1. This leads to this eigenvector. You can do something similar for the third eigenvalue. This is the system of equations. Again, here we have done some row operations here, right, to obtain an equivalent system. We have fixed v31 to 1, and then by looking at equations 3 and 2 we have defined v32 and v33, and this is then the eigenvector v3 associated to the eigenvalue lambda 3. Here we want to use a decomposition of A, that is Q lambda Q transpose. We can do this because this matrix is positive definite and well, symmetric, right? In lambda we put the eigenvalues, and in the matrix Q we have to use the eigenvectors, but we have to normalize them to give them a unit length, right? So if you do this, this is the matrix Q, right? Q1, Q2, Q3, and then we want to obtain a factorization R transpose R. So you can see that you should take R is equal to, between quotes, the square root of lambda. Since the eigenvalues are positive, well, this is well defined, and then multiply by Q transpose. And if you do this, this is what you obtain. If at the time of the exam you do not have the time to compute this, this is not a problem. Just leave it like this. This is really good enough. I can see that you can work with eigenvalues and with eigenvectors.